Our next section now is net force, or sigma F. Sigma F, as we know, equals MA. So now let's look at the left side. So the sigma F, as I said before, is the sum of, and it's sometimes written as F net. It just means all of the forces added together. So the arrow above reminds us that it's a vector. So like velocity, direction matters. We won't always write the arrow, but you need to remember it's there. It means that when you add the forces, you have to add them like vectors. Forces have direction, and they can cancel out. So for example, we have a 5-kilogram object is being acted on by a 20 Newton force to the right, and a 30 Newton force also to the right. What is the net force on the object? So first we'll draw a free body diagram. You need to remember that because we're going to be doing a bunch of those. They basically consist of a dot, and which we have right here, and that represents your object. And then you're going to have arrows that represent the forces. The direction of the arrows represent the direction of the forces, and their length is roughly proportional to their size. So as you can see, they drew F1, so this was that 20 Newton one that they talked about in the problem up here. So they drew that on there. Next thing they did was they drew, okay, we also have a 30 Newton force to the right. And if you notice, 31 is bigger than the 21. And then next, all they did was they took this and they said, okay, well, since they're both going to the right, we can put them end to end and we can get our total force right there. This is what they did over here. So now we know the sum of the vectors is going to be this first one, plus this second one, since they're in the same direction. And now we're going to plug that into our equation. So we've got our sigma F is equal, remember that's the sum of the forces, so it's F1 plus F2. And now they just went in the givens and they put what they were, 20 and 30, and then they added them. And since they are both to the right, when you add them, it's going to be to the right. And we know that because it's a positive answer. So now in this example, we've got two forces act on an object. One force is 40 newtons to the west, and the other force is 40 newtons to the east. What is the net force acting on the object? If you remember from a compass, you've got north, south, east, and west. So if we think of the west and the east like a number line, so what we have is our first force is 40 newtons to the west, and if we look at the number line up here, we can say that our F1 equals negative 40. Since it looks over here like our number line, west is negative, and that's newtons. And we could say our F2 is equal to 40 newtons, positive. So what's the net force acting on the object? If we know our net force equals F1 plus F2, and if we plug our numbers in, we get negative 40 plus 40, which gives us 0 newtons. Now to the next one. Two forces act on an object. One force is 8 newtons to the north, and the other force is 6 newtons to the south. What is the net force acting on the object? So we've got our F1 is going to equal 8 newtons, and since it's to the north, we know that north is up and south is down. So we can think of this as the positive, this is the negative. So now F2 equals 6 newtons to the south, so we can make that negative 6 newtons. So if sigma F equals F1 plus F2, we can plug in our 8 plus negative 6, which is going to give us sigma F equals positive 2 newtons. And since it's positive, we know it's going to be to the north. So that is C. Now, Newton's second law of motion. So now we need to look at the right side of the equation, our MA. Mass is a scalar, so it doesn't have a direction. You just have that mass, it doesn't change. And acceleration does have a direction, it is a vector. The direction of the acceleration vector is always the same as the direction of the net force. So if you think about sigma F equals ma, whatever direction the acceleration has is going to be the same as sigma F. Because mass doesn't have a direction, so it's not going to change anything. So for example, we've got same problem as before, our 5 kilogram object, 20 Newton force to the right and the 30 Newton force to the right. So we found the net force in the object to be 50 newtons to the right. So now we want to find the acceleration. So what we need to do is we've got sigma F equals ma. We want to get the a by itself, so we would divide by m, divide by m. Now a equals sigma F over m, which is going to equal 50 over 5, which is going to equal 10 meters per second squared. So now force is a vector, so sigma F equals ma is true along each coordinate axis. So this means we can add up all the forces in the vertical direction, as those will equal ma in the vertical direction. So if you look, we have F1 over here and F2 over here. So these added together have to equal ma vertically. So if you look, that's what we have over here. So that means our F1 minus our F2, since it's in the opposite direction, that's why it's negative over here, equals ma. And we know, in this case, they're equal, because F1 minus, if it's not moving, that means our acceleration is 0. So that means F1 minus F2 is going to equal 0. And you could do the same thing in the horizontal direction. So if you notice, in our picture over here, it says that it's accelerating to the right, and that's what we have over here, by 1 meters per second squared. And there's only one force going that way. So if our force F3 equals ma, and there's nothing on this side at all, so there's nothing to write on for F4 or anything else, our mass was 2, and our acceleration is 1. So that means that when you multiply them, our F3 is 2 newtons. So now we've got a force F1 equals 50 N acts to the right on a 5 kilogram object. Another force, 30 N, acts to the left. Find the acceleration of the object. So we have our little free body diagram over here. We've got F1 going this way at 50 newtons. Then you've got F2 going this way at 30 newtons. And we know sigma F equals ma. And our sigma F in this case is going to be, this is the positive side, so we know it's going to be 50 minus 30 equals, and in this case our mass is 5, and we are looking for a. So to get our a by itself, we would have to divide by 5, divide by 5, cancel that out. So now a equals 50 minus 30 over 5, which equals 20 over 5, which equals 4 meters per second squared. Next one, a force F1 equals 350 newtons, which is upwards on a 20 kilogram object. Another force F2 equals 450 newtons, pulls downwards. So we have our object over here. We've got 350 newtons going up. And we have 450 newtons going down. And we know our mass equals 20. And as we said, F1 equals 350. And F2 equals 450. Oops. Equals negative 450. So now you've got sigma F equals ma, which is going to be F1 plus F2 equals ma, divided by m to get the a by itself. And now we just have to do a equals our F1, which was 350, minus 450 over 20. which gives us 100 negative over 20, which is going to equal negative 5 meters per second squared. And that makes sense because if you look, it's going down, which is why our acceleration is negative. All right, an object accelerates downward at a rate of 4.9 meters per second squared. The downward force on the object is 500 newtons, and the upward force is 250 newtons. What is the mass of the object? So now we've got our free body diagram, and we have going down at 500 newtons, and there's an upward force of 250. And we know the acceleration is going down at 4.9. And we want to look for mass, so if we've got sigma F equals ma, and we know that to get our mass by itself, we have to divide by A. So now mass equals sum of our forces, so F1 plus F2 over A. And now we just have to plug them in. So our F1 was negative 500 because it was down, plus 250 over negative 4.9 because our acceleration was also down. So now that's going to equal negative 250 divided by negative 4.9. And our mass will equal 51.02 kilograms.